Think about time for a second. You know, that steady march forward. Cause always preceding effect.
Yeah, it feels like a pretty fundamental law of the universe, doesn't it?
It really does. But what if we took the ultimate zoom lens, like way beyond atoms, even beyond quarks?
Down to the Planck scale.
Exactly, down to the incredibly minuscule Planck scale. And here's where things get really interesting,
Hmm.
where the seemingly unshakable rules of reality might just, well, wiggle a bit.
And what's fascinating here, looking at our sources, is this idea that at this most fundamental level, the very fabric of space-time,
Well,
it might not be that smooth, predictable stage we experience every day.
right?
Our sources for this deep dive, we've got a study guide on Planck-scale physics, a really thought-provoking paper on something called the Planck switch, and even some more imaginative narrative explorations.
Yeah,
They all seem to point to a reality at the absolute bottom that's just far more dynamic and, frankly, stranger than we can easily picture.
totally. And that's precisely what we're diving into today. This is really tailored for you, the learner, who's keen to, wrap your head around some seriously complex stuff.
Planck-scale physics, implications for time, causality.
Right. Without getting lost in a jungle of equations, we're really aiming for those aha moments delivered straight to your ears.
And if we connect this to the bigger picture, I mean, understanding the Planck scale isn't just some abstract intellectual game.
Yeah, definitely not.
It's about trying to uncover the deepest secrets of how the universe actually operates. And these sources, they suggest that by grasping the rules at this level, we might one day unlock possibilities that currently sound like pure fantasy.
Like fundamentally new ways of interacting with space-time itself.
Potentially, yes.
Okay, so hold on tight, everyone. Our exploration today is going to take us through the bizarre behavior of light and gravity when you shrink way, way down.
To the tiniest imaginable scales.
Then there's the concept of space-time being built from fundamental pixels, almost.
That's a key idea, yeah.
A wild thought experiment about potentially flipping the order of cause and effect.
The Planck switch idea.
And the truly mind-bending notion of using light itself to warp space and maybe even time.
It sounds like science fiction, absolutely.
It really does. But don't worry, we're here to be your expert guides. We'll extract the key insights, make sense of it all.
Get ready for some surprising facts and explanations that'll hopefully click without, all the overwhelming technical jargon.
Ready to jump in?
Absolutely. Let's start with gravity. Why does it get so weird when we zoom down to the Planck scale?
Okay, so the first key thing our sources really emphasize is that in incredibly strong gravitational fields,
Yeah.
think near black holes or the very early universe,
By extreme conditions.
gravity stops acting in that straightforward linear way we're used to. It's not just more mass equals proportionally more gravity.
That's exactly right.
Yeah.
The Einstein field equations, the bedrock of general relativity, they are inherently nonlinear. We'll think of it like this. Normally, you add a weight to a scale. It just adds that weight's effect. Simple. But with gravity in these extreme conditions, the weight of the gravitational field itself actually contributes to the overall gravity.
Oh, okay.
It creates a kind of feedback loop. The effect influences the cause, which influences the effect. It gets complex.
And this nonlinearity, it has some pretty strange consequences for photons, right? For light particles.
Oh, definitely. They don't just sail through these intense gravitational areas unaffected.
Not at all.
Far from it. Their paths become significantly curved. And crucially, these effects don't just neatly add up, like you might expect.
How so?
Well, for example, a photon can lose or gain energy depending on the gravitational landscape it traverses. That's redshift and blueshift.
Right.
Their paths get bent. That's gravitational lensing.
We see that with galaxies.
Exactly. And in really extreme fields, even the photon's own energy can subtly warp the space-time around it. That's called back reaction.
Ugh.
So, yeah, no simple layering of effects. Everything gets tangled up in this dynamic, curved space-time.
So it's all intertwined. And this is where things get even more peculiar, right? At the Planck scale itself, space-time might not even be smooth anymore.
Precisely. Some leading theories propose that at this unimaginably small scale, space-time might actually exhibit a kind of foamy nature.
Foamy, like bubbles.
Sort of. The idea is that quantum fluctuations could be so intense that the very concept of a clear, well-defined path for a photon just starts to lose meaning.
That's hard to picture. A stark contrast to the smooth, continuous fabric we usually imagine.
It really is.
Okay, foamy spacetime. That's a wild image. But the sources also explore another mind-bending concept. Spacetime is being made up of pixels.
Right, not screen pixels.
No, something more fundamental.
What's fascinating here is that several prominent theories trying to unify quantum mechanics and gravity, the big challenge in physics, suggest that space-time isn't a smooth continuum. Instead, they propose it might be quantized, meaning it's composed of discrete fundamental units, these pixels of geometry, if you like.
So if you could zoom in close enough, space-time wouldn't be like a smooth ramp, but more like a staircase with incredibly tiny steps.
That's actually a helpful way to visualize it, yeah. And different quantum gravity theories have their own ways of describing these pixels.
Like what?
Well, loop quantum gravity, for instance, it envisions space-time built from fundamental geometric building blocks woven into structures called spin networks.
Spin networks.
Yeah, and a key insight there is that even properties we think of as continuous, like area and volume, might actually be granular at the most basic level.
So space itself is kind of lumpy at the tiniest scale.
In a sense, yes, fundamentally changing how we think about geometry.
Okay,
Then you have causal dynamical triangulations. That suggests space-time emerges from these tiny geometric elements, almost like microscopic Lego bricks fitting together.
Huh, space-time Legos.
Kind of. And causal set theory takes a different approach. It views space-time as a discrete collection of fundamental events, partially ordered by cause and effect.
So more about the relationships between points.
Exactly.
Yeah.
It focuses on the causal structure linking these fundamental space-time atoms.
It sounds like they're all kind of circling a similar core idea, though.
They are.
That the smooth space-time we perceive is just an approximation at our scale.
And if you could zoom in enough, you'd see this fundamental graininess or structure.
Like looking closely at a fabric.
Precisely. From a distance, it looks smooth. Up close, you see the threads. These theories suggest space-time has a similar kind of underlying discrete structure.
Now, something that's always seemed a bit counterintuitive to me is gravity. It feels so dominant, right? Keeps on the ground, holds galaxies together. But physics says it's actually weakest of the four fundamental forces at everyday scales.
That's correct, comparing particle interactions.
But the sources say this flips at the Planck scale. Gravity becomes dominant. How does that work?
Yeah, that's a really crucial point. At the intermediate scales we experience, you're right, electromagnetism, the strong and weak nuclear forces, they're much more powerful than gravity between individual particles.
Okay.
However, gravity's influence is determined by mass energy, and at the Planck scale, quantum uncertainty becomes incredibly significant.
Quantum uncertainty. Right. The Heisenberg principle. You can't know everything precisely.
Exactly. And at these incredibly tiny scales, this uncertainty principle leads to enormous fluctuations in energy density within minuscule regions, just popping in and out of existence, essentially.
They're huge energy spikes in tiny spots.
Massive ones. And even though the gravitational pull of a single, say, Planck mass particle might still be technically weak because Newton's constant g is small,
Right.
the sheer concentration of energy packed into such a tiny volume causes significant warping of spacetime.
I see. So it's not that the force itself gets intrinsically stronger per particle,
Not necessarily.
but there's just so much concentrated energy fluctuating in such a tiny space that its cumulative gravitational effect becomes the main player.
You've got it. The quantum fluctuations of space-time itself become incredibly energetic and chaotic at this scale. And gravity is the force that governs how mass energy curves space-time.
Okay.
So despite its relative weakness particle to particle at larger scales, down at the Planck scale, gravity takes center stage in this wild quantum dance.
This is all really stretching my understanding of reality. Okay, but now let's delve into something that sounds like pure science fiction. This concept of the Planck switch
Right.
and the possibility of reordering cause and effect. Okay, let's unpack this slowly.
Well, first off, the Planck switch is presented as a thought experiment. It's a conceptual tool, really.
A way to explore.
Exactly. To explore the fundamental nature of causality under conditions approaching the Planck scale. It's about asking whether that strict before and after relationship we always assume might become more flexible, maybe even probabilistic, at these extreme energies and tiny scales.
Okay, and the setup involves entangled photons.
Yes, those quantum-linked particles.
And this hypothetical Planck engine. What is that supposed to be?
So the Planck engine is envisioned as a device purely theoretical for now. Of course, that could create a highly localized region with extreme space-time curvature.
Like really intense gravity in a tiny spot?
Extremely intense.
Yes.
Where the very structure of the quantum vacuum itself is being manipulated near the Planck scale. Think of it as a microscopic machine for warping space-time in crazy ways.
Okay, so you have these entangled photons linked together. You send them through or near this Planck engine. What's the core idea about reordering cause and effect?
The central idea, the speculation, is that the intense gravitational and vacuum influences from the Planck engine, particularly through what are called nonlinear interactions.
Nonlinear again.
Yes, that comes up a lot here.
Yeah.
These interactions could probabilistically influence the temporal order in which measurements made on those entangled photons appear to affect each other.
Whoa, so wait, probabilistically influence the order.
Potentially. Now, it's crucial to understand this isn't classical time travel. You're not going back to change the past.
Okay, good.
It's more about manipulating the fundamental causal structure itself, so that the before and after these specific quantum events could become ambiguous or maybe even depend on the conditions the Planck engine creates.
So not changing history, but fuzzing up the sequence of events at the quantum level in that extreme zone.
That's a good way to put it. Like the arrow of time for those tiny interactions could become a bit blurry or probabilistic right there.
Okay. And our sources highlight something called nonlinear electrodynamics, NLED. How does that fit in?
Right. So standard electrodynamics, how we usually understand light, is linear. Photons don't directly interact with each other.
Yeah, they just pass right through each other.
Precisely.
Yeah.
But NLED theories, like one called Born-Infeld electrodynamics, they suggest that under the extreme conditions you might find near the Planck scale, electromagnetic fields might start behaving non-linearly.
Meaning photons could interact.
Yes, potentially allowing photons to interact with each other and also interact with the vacuum itself, like influencing the virtual particles that are constantly popping in and out.
Okay, here's where it gets really interesting, maybe. So this nonlinear behavior could be the key. The mechanism for how the Planck engine might actually do this causal reordering thing on the entangled photons.
That's the speculative leap, yes. This nonlinear interaction could provide a potential mechanism. A photon passing through the Planck engine's intense field might have its properties altered in a way that probabilistically affects the subsequent measurement of its entangled partner, potentially scrambling the usual A influences B temporal order.
Wow.
It's about this complex dance between extreme curvature, quantum entanglement, and these nonlinear field interactions, all happening at the most fundamental level.
This Planck switch idea, it opens up some seriously mind-bending possibilities. But it's all highly theoretical for now, right? Like, how could we even begin to investigate this?
Good question.
That's where quantum computing comes in, according to our sources.
Absolutely. I mean, given the extreme conditions, the quantum nature of it all, direct experiments are currently way beyond us.
Right.
But advanced quantum computers, maybe guided by AI, offer a really promising route to simulate these complex nonlinear effects.
So using quantum computers to essentially build virtual Planck engines in the simulation and see what happens to simulated photons.
That's the basic idea. By creating really sophisticated quantum simulations, we could potentially model these intricate nonlinear interactions.
And explore what they do.
Yeah, explore their impact on fundamental things in quantum information, like qubit stability, how quantum gates behave under these conditions.
And the sources suggest this simulation work could actually lead to breakthroughs in quantum computing itself, not just using it as a tool.
Precisely. Simulating these Planck scale affects the strong gravity, the dynamic vacuum. It could inspire completely new ways to manage and maybe even enhance qubits.
Qubits being the basic units of quantum computers.
Right. For instance, if we get a deeper understanding of how these nonlinear dynamics affect stability, we might discover novel techniques to protect qubits against decoherence.
Which is that frustrating loss of quantum information, the big challenge.
Exactly. That's a major hurdle right now, keeping qubits coherent long enough for complex calculations.
Okay, what else?
Furthermore, these simulations could inform the design of more powerful nonlinear quantum gates.
Instead of the mostly linear ones we use now.
Yeah, and those could potentially perform certain types of computations much more efficiently. And looking even further out, simulating these multi-level interactions could maybe pave the way for developing multi-level quantum systems called qubits.
Qubits.
Yeah, they can store and process significantly more information than standard two-level qubits, higher dimensionality.
So it's this interesting loop. Trying to simulate the most fundamental physics could actually revolutionize our most cutting-edge technology.
It's a fascinating possibility.
And the role of AI in this. Is it just running the simulations?
Well, potentially more. AI could help optimize these incredibly complex simulations, analyze the huge amounts of data they produce, identify subtle patterns.
And maybe even help design things.
Possibly. Design entirely new types of qubits or quantum computer architectures based on what we learn about how the universe works at its smallest scales, using nature's rules to build better tools.
Okay, so we've gone from foamy space-time to maybe tweaking causality with a Planck switch to using quantum computers and AI to study it. But the sources also hint at some truly, well, out there speculative technologies.
Way out there, yeah.
Let's talk about spaceships powered by light and chronotonic symphonies. That sounds like something straight out of a movie.
It does, but it's presented as a fascinating, though highly speculative, extension of these fundamental ideas. Imagine a spacecraft using what the source material calls a photon warp core.
A photon warp core, okay.
The basic concept involves generating and manipulating incredibly intense beams of light, but in a very precise, structured way.
So not just like a giant flashlight pushing the ship.
Oh, definitely not. The idea is more subtle. By creating a sophisticated lattice or configuration of these extremely high-energy, phase-locked photon beams.
Phase-locked, meaning they're perfectly synchronized.
Exactly. The ship could potentially interact with the fabric of space-time itself through those nonlinear effects we discussed earlier.
Like vacuum polarization, virtual particles.
Right, and potentially even direct curvature-induced photon interactions if things get extreme enough, near the Planck scale.
And the goal of this interaction would be?
The speculative goal is basically a warp bubble, but powered by light.
Like in Star Trek, but using focused light energy instead of, exotic matter with negative mass.
That's the comparison, yes. By carefully controlling the energy density and a specific pattern of these photon beams, the notion is to create an anisotropic distribution of energy momentum.
Anisotropic, meaning?
Uneven.
Different in different directions.
Exactly. That uneven distribution could potentially warp space-time around the vessel, contracting space in front, expanding it behind.
Creating a warp metric.
Effectively, yes. Generating a warp-like metric that could, in theory, allow for faster-than-light travel relative to distant observers without violating local laws of physics within the bubble.
That's incredible. But then there's this concept of chronotonic symphonies. That sounds even more enigmatic. What's that about?
So the idea of chronotonic symphonies comes up as a potential way to navigate through this warped space-time created by the Photon Warp Core.
Okay.
And perhaps even to subtly influence the flow of time within that localized region.
Influence time flow. How?
Well, think of them as precisely orchestrated sequences of quantum-structured energy, modulations in the photon beams. They carry not just energy, but also information about the space-time curvature, about quantum entanglement states. It's not conventional music.
No violins.
No violins. But highly structured patterns of light, curvature, and entanglement.
So not actual musical notes, but carefully designed patterns of light energy meant to interact with space-time itself.
Exactly. And the analogy drawn in the source material to ancient transition songs, like from the Bardo Thodol, the Tibetan Book of the Dead, or similar traditions, it's quite thought-provoking.
How so?
Just as those ancient texts provided a kind of map or framework for navigating transitions between different states of being or consciousness.
Right.
These chronotonic symphonies are envisioned as potentially providing a framework for matter, maybe even consciousness, to navigate the extreme conditions of warped spacetime.
Like offering stability, guidance.
Yes, stability, guidance, and maybe a way to reintegrate back into normal spacetime safely.
That's a surprisingly poetic connection. Almost spiritual. Ancient maps for inner journeys meeting potential maps for interstellar journeys.
It is a striking parallel.
And the implication is that by mastering these symphonies, we could potentially not only warp space, but also subtly modulate the experience of time within that warp bubble.
That's the ultimate speculative frontier described. If space-time really is pixelated or quantized at the Planck scale, as some theories suggest, then perhaps by understanding the fundamental notes and harmonies of these chronotonic symphonies, the precise modulations of these photon fields, we could learn to essentially program or tune those fundamental quantum degrees of geometry. Which could potentially lead to what's been termed temporal engineering.
Temporal engineering. And that could mean what exactly? Locally manipulating space-time curvature for things like stable warp drives or maybe even traversable wormholes?
That's the kind of exotic possibility mentioned, yes.
Or even gaining some level of control over causal relationships. Which brings us right back to the Planck switch idea.
It does, doesn't it? The interconnectedness of these concepts, even at this highly speculative level, is truly fascinating. If we could genuinely engineer space-time at its most fundamental level, the possibilities, while still firmly in the realm of theoretical physics and maybe even beyond, they're just mind-boggling, creating artificial geometries, influencing the local passage of time.
And maybe, just maybe, influencing the fundamental order of cause and effect, even in a limited probabilistic way.
That seems to be the furthest edge of the speculation, yes.
Wow. This has been an absolutely incredible journey through some truly deep and, mind-bending physics. Before we wrap up, our sources included some thought-provoking questions for you, the listener, to consider.
Yeah, these are good ones to chew on. First, think about the different ways the leading quantum gravity theories imagine those fundamental pixels of spacetime.
Right, the loops in LQG, the strings, the simplices in CDT, the events and causal set theory.
What are the key differences in how they envision reality's fundamental nature at that scale, and what implications might those differences have for everything else?
Good question. And how do these non-linear effects at the Planck scale that we've been discussing, how do they really challenge our current, mostly linear understanding of physics?
And potentially open the door, conceptually at least, for these seemingly far-fetched technologies like the Planck switch or the Photon Warp Core.
It really makes you reconsider the boundaries of what might eventually be possible, even if it's centuries away.
And what about that parallel between ancient rituals for guiding transitions in consciousness and this modern scientific concept of chronotonic symphonies as guides through extreme spacetime?
Yeah, that connection.
Could there be some deeper underlying principle about how we navigate fundamental shifts in reality, whether they're internal or external?
That's intriguing to ponder. And finally, maybe one of the most profound questions raised. If we were to ever gain even a limited ability to manipulate causal structures at the Planck scale, what fundamental principles should guide that? What kind of ethical responsibility would come with such power?
That's huge. Ethical temporal design, as it were.
Yeah.
Okay, let's just briefly recap the key insights from this deep dive.
Please.
We've explored the nonlinear way gravity behaves at the Planck scale, this compelling idea of a granular, pixelated spacetime.
The foamy, lumpy reality.
Right. The tantalizing is speculative possibility of influencing causality, hinted at by the Planck switch thought experiment. And these truly visionary concepts of light-driven warp drives and modulating time itself using chronotonic symphonies.
And we sincerely hope that this exploration has given you, the learner, a valuable shortcut to understanding some really cutting-edge physics.
And spark some genuine aha moments for you.
Yeah, all without feeling like you've just been drowned in incomprehensible jargon.
And maybe connecting it back to the bigger picture. Just consider the very essence of time itself.
Right.
Is it really that fixed, forward-moving river we perceive every day? Or is there a deeper, more intricate, maybe even malleable reality hidden underneath?
Is causality as absolute a principle as we tend to believe?
And what are the ultimate implications, the responsibilities, that come with even beginning to glimpse the universe at its most fundamental level?
These are massive questions, and we really encourage you to continue your own exploration into these fascinating realms: quantum gravity, nonlinear physics, the philosophical side of it all.
Absolutely. The journey of learning and discovery, it never truly ends.
Thank you so much for joining us for this deep dive.
We really hope it has ignited your curiosity and perhaps even shifted your perspective a little on the nature of time, space, and the very fabric of reality.